So what we've got here is a cylinder. It's got a radius of 62.5 millimeters, which means 2 times that gives you a cylinder diameter of 125 millimeters. It's got a 100 millimeter throat. It's got a 45-degree angle in this corner. It's a 90-degree corner there, which means the other angle in the other corner is 45 degrees as well. So if it's 125 millimeters across this line here, that means from that point up to the top there must also be 125 millimeters. So we're going to calculate this out. There'll be another drawing that has one that's graphically drawn out. You should be able to step up to the sheet with a wee bit of practice. Simply pick a sheet of metal up, lay the pattern out, without actually having to draw a front elevation with an end elevation and projecting all your lines across. So up here I've created a formula, or the formula, formulator for calculating the elevation, elevational height required to do the calculation. The formula is opposite equals adjacent times tan theta. So the angle 45 will be theta in this one. So down here I've done the calculation in red. Opposite side equals 125 millimeters, which is the diameter, times tan of 45 degrees gives us our elevational height of 145. Now, if you change this angle to less than 45 degrees, this dimension of 125 would head back towards 0. If you increased your angle above 45 degrees, 125 is going to go above, so it's going to be 125 plus. So you can work out whatever your elevational height is using this formula in red above us by putting in tan, whatever your angle is, and the 125 in my example would be whatever diameter you're using, and that will give you an elevational height, which is what we're looking for. Once you've got the elevational height, I've got this factor plotting chart. We're using 12 points, so I've got the 12 points here in yellow. 0, the line number 0 at this point has no increase whatsoever, so that stays at 0. If you come back over here, line number 6, which is the 1.0, so it's 1. So from 125, if you times 125 by 1, it stays at 125. So line number 6 stays at 125. Line 0 is 0. If we come over here, point number 3 is actually 0.5. We come to the center line here. From the imaginary line up to the angle is basically half, or it is halfway of 125. So 0.5 over here on the left hand side times 125 gives you an elevational height here of 62.5 millimeters. So I've done all the calculations in this next chart down. You can see that. So 0.0 times 125 is 0 on this elevational height side out here. The next factor is 0.067 times 125 gives you a height of 8.375. And if you work down through the chart using the factors, you can do all the calculations for your elevational gains from this information here. So that's what you're going to put into the chart, do the calculation, work out your elevational heights. I've worked out my roll length. 125 times pi gives me a length of 392.6990817. You're not going to be working it out that accurately. That would be absurd. You will try to work it out to say 392.7. Even that's going to be a big ask with a compass. Probably got a blunt pencil in it. And then if I divide my 392, which is my rollout length, by 12 equal spaces, I come up with this figure here of 32.72492,347. Once again, you will try and work towards 32.7. So we've got the information we need. So I'm going to start drawing it. So I'm going to put a line down. Just going to pick anywhere on the page, on the sheet. It had to be 392.6990817 long. From there, it's got the cylinder. If we take this cylinder, this bottom part, which is actually a rectangle, and we roll it out, it's 100 millimeters high, so I can offset that 100 and just lay that in and put my ends on it. and on the other end. Now that cylinder on the base there could be 1 millimeter long, it could be 53 kilometers long. It doesn't matter. It simply stays as a rectangle panel. It's 100 mil high. This line is 100 mil long, and it's rolled out to a length of 392.7 millimeters. So from there, I do my offsets across it, which is my 12 parts that I'm looking for, or 12 equal divisions, and I'm going to step those across. I'm going to number these, so I've got another drawing here with number inserts on it to try and speed this whole process up for you, because it'll just take too long otherwise. So I'm doing a fishtail pattern, copy with a base point, which is that point there, go into my drawing, paste it. So there's my numbers for rolling it out. So my maximum distance that is the 125, so I need to offset 125 millimeters, push the wrong number, 125. There we go. I'm going to extend all these lines. You would do this with a T-square and a pencil, of course. Actually, sorry, I needed to extend those other two as well. Like a twit, I didn't do it. There we go. Now, so if we come back over here just quickly, our first offset is, if I go into pan, our first offset is this figure here of 8.375. So you would be drawing something about 8.5 millimeters if you could. So offset of 8.375. There's my first one. Go into pan again just to show you. My next offset for line number 2 is 31.25. So offset 31.25 from that line there. My next one, I said to you before, half of 125 for line number 3. Point number 3 is point, go into pan, 0.5 times 125 gives you 62.5. Offset 62.5. If I carry on to line number 4, it's 93.75. Better go on and show you that. So 93.75. Then I'll do my next one at 116.625, and we've already put our top one at 125 anyway. So offset, what do I say? 93.75. And the last one is 116.625. Twit. Put an offset in of 116.625. So there we go. We've got what we're looking for, so we can start to lay our pattern in immediately into that. Our joint line was on line number 3, so this being line number 3, this position here, this is halfway, and that's what we're looking for here. So halfway, we're going to step from 3 up to 4, 5, 6, back down to 0, and then back to 3. So doing that on a spline. 3, up to 4, up to 5, 6, 5, 4, 3, 2, 1, 0, 1, 2, there we go. So there's our curve. All these lines going across here are actually projection lines. You draw them, try and draw those with a 4H pencil or something. And once you've got your curvature that I've just put in, you would draw that on a thicker pencil, maybe a Let's just drop these onto projection lines for a start before I forget what I'm doing. You would draw that on a 2B or something if you were drawing it on a page, or if you're doing it straight onto metal, like I'm hoping you'll learn to do, you can use the scriber, of course. So just trimming all the lines out that aren't necessary. That's our line that we were looking for. So I'm just going to get rid of everything above that line. Rip that one off there like that. So number 3 was our center line. I didn't quite put that, it's on the opposite side, but it's a projection line. So there's our actual pattern of what you are looking for. Simply calculated, not drawn out graphically. Nothing wrong with drawing graphically a pattern out, of course there's not. But if I turn off my projection lines, that's basically what you would have for a pattern. And it's simply being calculated instead of drawn graphically. So if you can start to follow the, do a couple of calculations to work out your elevational height, which is what you're looking for over here. Depending on your angle, this is the information you're looking for. The 100 millimeters was simply put across the bottom here as a rectangle cylinder, and then we'll put our curvature above it. All the information is on the screen for you. The formula is there and how to do it. The factor plotting chart, which has the data in it. I've used 12 points only, and we'll go back to put that on just for a moment. So 12 points is 0 to 6, back down to 0. Let's say you had something that was 2 meters in diameter, and you felt that you needed more points in it. You could use 24 points. This chart here, so this would be 0. You'd have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then back round to 0 on this side. So you can use as many factors as you want. 32, you might have something that's 4 meters in diameter, and you just need simply to put more points in. This is how a computer draws it within the computer. They have this formula inside the computer. They have this formula, sorry, they have these plotting points, and you can work out the rollout length and your spaces, and that's all you need to do to actually develop a fishtail pattern for an offset, anything like that. Could be a piece of ducting coming off a flat surface, could be anything, but that's how you're going to develop it. Look at my other videos to see how to draw it out graphically, and you can't go wrong. So I will save that and stop there. Thank you.